Something is coming, not a comet, not a dying star, not some rogue piece of rock hurtling through the dark. 1 trillion stars aimed right at us, right now, while you're sitting there watching this. We've known about this for decades. We've done the math, run the simulations, mapped the trajectory down to the decimal place. We know exactly what's going to happen. The question isn't if, it's what. The Milky Way is home. We talk about it like it's been here forever, like it always will be. A permanent fixture of existence. That's not how galaxies work. That's not how anything in the universe works. Right now, in what astronomers call the local group, our galaxy is one of roughly 54 galaxies, all held together by gravity. Most of them are small, dwarf galaxies, satellite galaxies, things smaller than the Magellanic Clouds you can pick out from the southern hemisphere. But 2 of them are giants. The Milky Way and Andromeda. For billions of years, these 2 galaxies have dominated this corner of the universe, and for that entire time, every single year of it, they have been moving toward each other. Andromeda is closing in at roughly 110 kilometers per second, about 250,000 miles per hour, and it has been doing that for a very, very long time. On a clear autumn night, away from the city, somewhere actually dark, look northeast. Find the constellation Andromeda. There's a faint, slightly elongated smudge up there. Easy to miss, easy to write off as a cloud. It's not a cloud. That is an entire galaxy. 1 trillion stars sitting right there, visible with your naked eye, moving toward you at 110 kilometers per second. In about 4 billion years, that faint smudge is going to fill the sky from horizon to horizon, if anyone is still around to see it. Let's actually look at what we're dealing with, because Andromeda isn't just some neighboring galaxy drifting too close. It's bigger than us. The Milky Way has somewhere between 200 and 400 billion stars. That number is already so large, the human brain can't really hold it. We just kind of nod at it and move on. Andromeda has approximately 1 trillion. Our galaxy stretches about 100,000 light years across. Andromeda is nearly 220,000. In raw size and star count, Andromeda wins. But here's where it gets strange. The Milky Way might actually be more massive overall because of dark matter. The dark matter halo around our galaxy extends hundreds of thousands of light years beyond what we can see. Some estimates put our total mass slightly above Andromeda's, even though they have more stars. And here's the part nobody talks about enough. At this very moment, those dark matter halos are already overlapping. Even at 2.5 million light years apart, the outer edges of our gravitational reach have been brushing against Andromeda's for a long time. This collision, in a very real sense, has already begun. Andromeda was first seriously studied in the 1920s by Edwin Hubble. Before that, astronomers called objects like it spiral nebulae and assumed they were clouds of gas inside our own galaxy. Hubble measured the distance using Cepheid variable stars, pulsating stars whose brightness acts like a cosmic measuring tape. What he found changed everything. That tiny cloud wasn't inside the Milky Way at all. It was another galaxy entirely, sitting millions of light years beyond our outermost stars, an island universe of its own, one measurement. Everything we thought we knew about where we live, rewritten overnight. But Hubble noticed something else, something that took decades to fully understand. Andromeda wasn't moving away from us like almost everything else in the observable universe. It was moving toward us. Most galaxies are receding because the universe itself is expanding, space stretching, carrying everything along with it. But Andromeda and the Milky Way are gravitationally bound, locked together. The expansion of the universe isn't strong enough to pull them apart, so they're falling toward each other. Two objects in a gravitational relationship since the Big Bang, slowly, inevitably arriving at a conclusion. One more thing. This isn't just a two-body story. The Triangulum Galaxy, the third largest in the local group, orbits Andromeda closely enough that it may get swept up in the merger as well. About 40 billion stars. Smaller, but the simulations suggest it could shape how the final galaxy actually forms. There are more players here than most people realize. In 2012, a team using the Hubble Space Telescope nailed down the trajectory. Not an estimate, an actual measurement. They tracked Andromeda's proper motion, how much it was shifting sideways across the sky, not just bearing down on us. That sideways component, smaller than expected, much smaller, and that changed everything. A larger lateral speed might have meant a glancing blow. Close, dramatic, but not a true merger. The data said otherwise. The approach angle is nearly straight on. There's no grazing the edge. It's a direct hit. The first close pass happens in roughly 4 to 4.5 billion years. And collision is going to feel like completely the wrong word the moment you hear what actually happens. The distances between individual stars are so vast that the overwhelming majority will never touch. The nearest star to our Sun is Proxima Centauri. It's 4.2 light-years away. If you shrank our entire solar system down to the size of a dinner plate, Proxima Centauri would be about 8 kilometers from you. UNB stuff. That much empty space between neighbors, and the whole galaxy is built that way. Two galaxies running through each other is less like two brick walls smashing, and more like two enormous swarms of birds flying through each other. Mostly, nothing touches. The stars just thread past, in silence. But that doesn't mean nothing happens. Gravity doesn't need contact. When two galaxies interpenetrate, their gravitational fields tear at each other. The spiral arms shred. Stars that have traced the same quiet orbits for billions of years get flung onto entirely new paths they'll follow for billions more. Some get ejected entirely, thrown into the emptiness between galaxies, too far from anything to call home, drifting alone in the dark for billions of years. Both the Milky Way and Andromeda start producing these stellar refugees long before the galaxies ever fully merge. Astronomers don't have to imagine this. They can see it happening right now in other galaxies. The antennae galaxies. Two spirals, 45 million light-years away, currently in the middle of exactly this. Long streams of stars stretching outward like arms, enormous bursts of new star formation blazing through the system as gas clouds collide and compress. What Hubble sees there is a preview, a rough dress rehearsal for what's coming here. The simulation shows something else too. After that first pass, after the two galaxies fly through each other and start to pull apart, they don't just keep going. Gravity pulls them back. They swing toward each other again for a second encounter, then a third. Each pass takes hundreds of millions of years, and with each one, more energy bleeds away, more structure unravels, and the two galaxies edge closer to something permanent. The whole process, first contact to fully merged galaxy, takes something on the order of 4 to 5 billion years after that initial close pass. Here's something I want you to sit with for a second. We can tell with real accuracy what the night sky will look like from Earth across this entire event. Not guessing, we've modeled it. We know the sequence. Right now, Andromeda is a faint elongated smudge. On a very dark night, away from light pollution, you can just about make it out with your naked eye. Barely there. You could look right at it and miss it. In about 2 billion years, noticeably brighter, larger, you'd see it clearly without effort. In 3.5 billion years, unmistakable, a full galaxy, visible with the naked eye, with structure, dust lanes, the glow of 1 trillion stars arching across the sky. And then, as the first pass begins, roughly 4 billion years from now, the night sky becomes something no human eye has ever seen. Andromeda fills a huge section of the sky, not a point, not a smudge, an entire galaxy, spiral structure visible, blazing like a second Milky Way but bigger, both galactic cores burning simultaneously. Massive starbursts igniting across the frame as gas clouds compress and collide. The night sky in that era, our current sky, would look almost empty by comparison. There's a name for what's forming. Astronomers call it Milkomeda, a portmanteau of the two galaxies. Some prefer lactomeda from the Latin. Either way, what takes shape will be fundamentally different from either of its parents. The Milky Way and Andromeda are both spirals. Milkomeda will almost certainly be an elliptical galaxy. Those beautiful spinning arms, the structures you see in every photograph of a spiral, they'll be gone, disrupted by the merger, scattered into a smooth, rounded shape over billions of years. It's one of the most complete structural transformations a galaxy can undergo. Elliptical galaxies are generally older and quieter. They've burned through most of their fresh gas. New stars rarely form. What you're left with is an enormous collection of aging stars, slowly cooling. That's where this is all heading. One more thing the Hubble-based model showed, and it's counterintuitive. Even during the merger, the Sun and Earth are unlikely to be caught directly in any collision zone. The galactic cores will be violent, but stars in the outer arms of both galaxies will largely redistribute themselves into the new elliptical structure without ever physically approaching another star. The merger is, in many ways, a gravitational reshuffling more than a physical destruction. That doesn't make it gentle. The mechanism is just different from what you'd expect. There's one more chapter here, one that most discussions of this collision skim past or skip entirely. At the center of every large galaxy, there is a supermassive black hole. Ours is called Sagittarius A star, 4 million times the mass of our Sun. That sounds impossibly large, until you hear what's sitting at the center of Andromeda. Andromeda's central black hole, 100 to 140 million solar masses, 30 to 35 times more massive than ours. When these two galaxies finally fully merge, billions of years after the first close pass, those black holes won't immediately find each other. Their galaxies merge first. Stars settle into new orbits around the combined core. It'll take hundreds of millions of years more before the two black holes actually get close. But when they do get close, when they enter what's called a binary black hole system, they begin orbiting each other, spiraling inward, and as they do, they emit something, gravitational waves, ripples in space-time. Einstein predicted them in 1915. We detected them for the first time in 2015, when two stellar mass black holes merged somewhere out in the universe and sent a tremor through the fabric of space that reached us here on Earth. A signal so small it moved our detectors by less than 1,000th of the diameter of a proton. Think about that. The universe shook, and we felt it. Two supermassive black holes mergings, on the scale of the ones at the centers of the Milky Way and Andromeda, would produce gravitational waves that dwarf anything we've detected. The universe would ring from it. As they spiral inward, they drag everything with them: gas, dust, anything caught in their combined gravity, compressing it, heating it to billions of degrees. What results could be a quasar, one of the most energetic things in the known universe, an active galactic core so bright it outshines every star in the combined galaxy by a factor of trillions. When we look at the early universe, we see quasars everywhere. Those signals arriving from billions of light years away. That's exactly this process, playing out on a massive scale, over and over again, back when galaxy mergers were far more common. Two black holes finding each other, consuming everything around them, blazing for millions of years before finally going quiet. Here's where the scale of time becomes genuinely hard to sit with. By the time those two black holes are close enough to begin this process, our Sun will already be dead, already past its red giant phase, already cooled. The Earth, as a place capable of supporting anything, will have been gone for billions of years before the black holes even start circling each other. That tiny cloud wasn't inside the Milky Way at all. It was another galaxy entirely, sitting millions of light years beyond our outermost stars. An island universe of its own, one measurement. Everything we thought we knew about where we live, rewritten overnight. The question that probably hasn't left you through all of this, what actually happens to us? I want to give you a real answer. Earth and our solar system sit out in the relatively quiet suburbs of the Milky Way, about 26,000 light years from the galactic core, not near the center where most of the violence happens, out in the outer arms, out in the calm. The simulations say a solar system at our position would get perturbed during the merger, pushed into a new orbit around whatever structure is forming, possibly flung outward, possibly thrown into a completely different region of the new galaxy. But the odds that another star physically strikes our Sun, essentially zero, The sheer emptiness between stars protects us from that. The collision itself is not what kills us. Our sun is 4.6 billion years old. It has about 5 billion years of hydrogen fuel left. But in roughly 1 to 1.5 billion years, well before any galaxy comes near us, the sun will be hot enough that Earth's oceans start to evaporate. The planet becomes too warm for complex life long before Andromeda fills the sky. In about 5 billion years, the sun swells into a red giant, possibly large enough to swallow Mercury, Venus, and possibly Earth. The galaxy collision and the sun's death run on overlapping timelines. Earth isn't destroyed by Andromeda. Earth is destroyed by the star that has sustained it for its entire existence. That's not a coincidence. It's just stellar evolution. Whatever civilization might still exist in this solar system 4 billion years from now, and that's a staggering assumption even to make, would have the front row seat to the most extraordinary event ever visible from anything resembling home. The most spectacular show the universe has ever staged, and nobody here now will ever see it. Go outside tonight if you can. Find somewhere dark. Look for that faint smear in the constellation Andromeda. What you're looking at is 1 trillion stars, a galaxy larger than our own, moving right now as you look at it at 110 kilometers per second, aimed more or less at where we are. 4 billion years feels like a number that has nothing to do with us. And in one sense, it doesn't. But there's something unexpectedly clarifying about it if you let it settle. We live on a small rock orbiting a medium star in the outer arm of a spiral galaxy that is, right now, falling toward another galaxy. Every civilization that ever rose on this planet, every discovery, every war, every single person who ever lived, all of it happened inside a structure that is already actively in the middle of a 4 billion year collision. That makes us feel small, yes, but it also makes us feel like we're part of something that doesn't have a name yet, because it won't finish forming until long after our names are forgotten. Milky Way, whatever they end up calling it,